Let's look at OpenStack's College Physics, Chapter 3, Problem 27. A ball is thrown horizontally from the top of a 60-meter building and lands 100 meters from the base of the building. Ignore air resistance. A. How long is the ball in the air? B. What must have been the initial horizontal component of the velocity? C. What is the vertical component of the velocity just before the ball hits the ground? D. What is the velocity, including both the horizontal and vertical components of the ball just before it hits the ground? So we have to get organized. There's lots of information here, much of which is not actually given by the problem. It's just stuff that we know from theory. So I will first start out by drawing the diagram. I have, let's say that this is my ground level, and there is this building that is 60 meters tall, and a ball is given a horizontal velocity, so it starts in just the x direction, and I'm going to call this just v naught. As a result of this velocity, the ball will undergo projectile motion and land 100 meters away from the base of the building. So this is the information that the problem gives us. Now what we want to do is choose our x and y coordinate system so that we can be consistent and we know what the different values that we were given, the 60 meters and 100 meters are, in what direction and all that. So I'm going to say that this is my x, my positive x, and this is my positive y. So this way I can see that the origin of the coordinate system is at the base of the building, which means that the object starts from an x of 0 and a y of 60, and then the ball will land in 100 meters in the x direction, and it will have a final y of 0. Let's try to organize all of this in a table. So we want to have our x and y components. I'm going to write them here like that, and I'm starting out with the position. So the first thing I want is the initial position. So the x and y components are, okay, the object starts up here. So the x is 0, the y is 60. I'm going to write that here. Then the next thing we might want is the final position, and that is when the ball hits the ground. So that means that the y is now 0 and the x is this 100 meters. So I have 100 meters for x and 0 for y. The next things that we want are v initial, and we know that v initial is only in the x direction, and we don't know the value for it, but in my diagram I called it v naught, and I know that there is no velocity in the y direction initially. Then v final, we don't know anything about that as the problem states it, but from theory we know that since there is no air resistance, the x component of the initial velocity has not changed. So that means that we still have v naught as our x component for even the final velocity. And we do not know what v final y is, so I'll just call it v final y here. The other quantity will be acceleration, and since there is no air resistance, the acceleration in the x direction is 0. The acceleration in the y direction is acceleration of gravity. It points down, so that's why I'm going to put a negative sign. So it's negative 9.8 meters per second squared. And the last quantity is time. It doesn't have an x or a y component, so I'm just going to put a question mark in the middle here, so we don't think that we need an x in the x or t in the x direction and a t in a y direction. All right, so we have this organized. Now let's see what types of things we're looking for, what our unknowns are. Possibly all of the things that I didn't fill out in this table, but let's just go through the question and look at the statement of the question. So in part A, we're asked to find how long the ball is in the air. So we want the amount of time that the ball was in the air. In part B, we want the initial horizontal component of the velocity. So we're looking for this v naught. In part C, we want the vertical component of the velocity just before the ball hits the ground. So we're looking for the v final y. And in part D, we want the entire final velocity. So I'll write it like this as a vector. So I have to remember that I'm looking for both magnitude but also direction. So I want an angle for that. So those are my unknowns. Now I'm going to block off space here so I can basically rewrite my equations. So I'm starting out with my cheat sheet. These are my basic equations, but I want to see what kind of information I can get in the x and y direction. And I have to remember that in the x direction, there is a single equation that's useful for me, and that is v initial is delta x divided by delta t. So that's all I can do in the x direction. Now, in the y direction, I know that v final y is v initial y, and if I look at my table over here, v initial y is 0, so I'm going to leave that as a 0. I'm substituting in here. I don't have a velocity in the y direction initially. Plus at. A in the y direction is negative 9.8. So I have negative g, I'll just keep it in variable form, times time. So I reduced the first equation in the y direction to just this based on the values that I have in the y direction over here. Then the second equation tells me that final y, so if I read that off of my column here, final y is actually 0. So this quantity here is 0, is equal to initial y, and I have 60 meters for that, plus v initial yt. V initial is 0 as well, so that is 0 and that is 0, plus 1/2 times the acceleration of gravity times time. So I'm going to write the reduced form here. So I have 0 equals x initial, which is something that I know it's y initial in my case, plus 0 minus 1/2 gt squared. So that's what my second equation reduced to in the y direction. The third equation, v final squared in the y direction, that's something that I'm looking for over here. I don't know what that is. In part C is what I want to find it. That's equal to v initial in the y direction. So v initial in the y direction, that's 0. So I have that as 0. I know the acceleration is negative g, and delta y is y final minus y initial, so that's 0 minus 60. So I know many things in here. I'm going to rewrite that equation. So v final y squared is, like I said, 0. It starts with no initial velocity in the y direction, minus 2g delta y, and that will be the final y, which is 0, minus the initial y, which I'll just call y initial, so I keep it in variable form for now. So v final y squared then is 2gy initial. So just by looking at the equations and applying all of these various quantities that we wrote in our table, we reduce the equations to something very simple, and it's much easier to see how we can go about solving for the various things. So in the first part, I'm looking for the time that the ball was in the air. So in the first equation, I can't do that because I don't know this quantity and I don't know that quantity. In the second equation, I can't use that either because I don't know the final velocity in the y direction and I don't know the time. But the third equation here, I know everything here except for the time. So I will use that, and I will say, okay, for part A, y initial is equal to 1/2 gt squared, which means then that t is going to be square root 2y initial divided by g. So that is square root 2 times 60 meters divided by 9.8 meters per second squared. And when we plug in the numbers, we end up with 3.50 seconds. So we have our time here. Now, looking at all of the other equations, I know that I have time in all of them. So in the first equation, I know delta x and I know delta t. So I can solve for v initial, and that just so happens to be the second variable that we're looking for. So for part B, I know that v initial x is my v naught. That's what I called it in the diagram. And that is x final minus x initial. So from my table here, x final is 100 meters, x initial is 0. So I will write that down. 100 meters minus 0 divided by the time, which is 3.50 seconds. And when I plug in the numbers, I end up with 28.6 meters per second. So this quantity done in red is the x direction. Everything in blue is the y direction. I don't want to mix them. All right. In part C, now I'm looking for the velocity final in the y direction. So in this equation now, this is the quantity that I'm looking for part C. I know g and I know t. I found t in the first part. So I can use that equation and say that v final y is negative gt, or negative 9.8 meters per second squared, times the time, which was 3.50 seconds. And when I multiply those, I end up with negative 34.3 meters per second. All right, why is it negative? Well, it's negative because it is going to be going down. We have the final velocity. We know that the x component is v0 here as well. And then when I reconstruct this, the final velocity is this way, v final. Its x component is to the right, its y component is down, which is why we have a negative sign for it. All right, then in part D, I'll put it over here, we are looking for the entire v final. So that's the quantity that I drew here in black. This is my v final. So from the Pythagorean theorem, I see that v final is square root of v naught squared plus vfy squared. And I'm going to write that here. So v final, this is the magnitude, is square root of v naught squared. That's the x component in the of the final velocity, plus v final y squared. So that is, where's my v naught? 28.6 meters per second quantity squared, plus negative 34.3 meters per second quantity squared. Take the square root of this and end up with 44.7 meters per second. So the final velocity, just the magnitude, is 44.7 meters per second. And the angle, so I want this angle, I'll call that theta, and it will be the inverse tangent of the y component divided by the x component. So it's the inverse tangent of v final y divided by v naught. So theta is inverse tangent of v final y divided by v final x, and that is inverse tangent of 34.3 meters per second divided by 28.6 meters per second, and plugging in these numbers we end up with 50.2 degrees. So here we have the final velocity, which is 44.7 meters per second in a direction of 50.2 degrees below the x-axis. So I'm not going to write that in words here because I already drew the angle, so I know that it is below the positive x-axis.